If you don't remember 8 plus 1 equal to 9, please smash your head into the wall. Can you see what's happening? At all corners and at all faces. Yeah? Can you see this present at the face? All three lengths are different. This length is different from this length, is different from this length. So this is... Hello everyone. Welcome to Catalysis by Vedantu. My name is Pahul and I'm an alumnus of IIT Bombay. Now, this is the second class of solid state that you're doing with me. If you haven't attended the first class, the link is in the description. Please make sure you go and watch it before this one. Now, in today's class, we will understand about lattices. What is a unit cell? What are Bakwaas lattices? What are lattice points? What are the different parameters of a unit cell? And my dear friends, I guarantee you that today's class will be the most visually captivating class of chemistry that you've seen till date. We will see a lot of animations, we'll do a lot of nice diagrams and drawings and etc. So it's going to be a really fun class. So my dear friends, let's get into it and let's learn the new term lattice. Do you remember seeing this in the first class? This kind of a distribution? Yes? Do you remember which kind of a distribution is it for which kind of a solid? This looks like the distribution for an ionic solid because there are two types of constituents, okay? If there was only one type of constituent, then it would be either a networked solid or a metallic solid, right? But this one over here, since there are two types of ions that are repeating, this is an ionic solid and this particular one is a representation of NaCl. Fine. Small ones being sodium and the big ones being chlorine, respectively. Small ions sodium, big ions chlorine, obviously, right? Na positive, Cl negative. Now, my dear friends, when you zoom into a crystal of NaCl, this is what you see. This is what? This is the three-dimensional arrangement of sodium and chlorine ions in space, right? Three-dimensional arrangement of the particles of the solid in space. Can you see the three-dimensional aspect of it? Do you see that this basically looks like a cube, right? Cube jaisa hai na ye? Can you see? So it's basically three-dimensional. It's represented on a plane on this blackboard, but this is essentially what? A three-dimensional representation. So the three-dimensional arrangement of the particular points of the solid in space is known as a lattice. Okay. Now let me give you the bookish definition of it also. So simple definition is three-dimensional arrangements of the particles of the solid in space is called a lattice. Of course, when you zoom it in. But let's come to the bookish definition that I've taken from the NCERT itself. If the three-dimensional arrangement of constituent particles in a crystal is represented diagrammatically, in which each particle is depicted as a point, the arrangement is called a crystal lattice. Okay? So, point over here being that instead of making those spheres, yeah, on the last page we had those spheres arranged in space, right? So instead of making those spheres, if I just make points, okay, if I just make points, something like this, yeah, I'm just giving a broad idea. If this is the 3D arrangement of a certain crystal and I've marked the points, then these points, the arrangement of them in three dimensions is known as a crystal lattice. Okay? Fine. So this is the bookish definition. You can write it down. Same. Okay? Same definition written over here. Just another visualization for you. Yeah? So you can write it down. You can pause the video over here. Please take notes. Now, I always say that you have to take notes. But in today's class, there are going to be a lot of diagrams like this, a lot of animations as well. So try to make some of them in your notebook, but I'm sure you won't be able to make all of them. So don't worry. For today's class, I will give you the PDF. Okay? Where will I give you the PDF? At the end of the class, there is a Telegram link that I'll share with you. I will share the PDF of the class over there. Fine. So don't worry. Today's class is an exception. So if the three-dimensional arrangement of constituent particles in a crystal is represented diagrammatically, in which each particle is depicted as a point, the arrangement is called as crystal lattice. Three-dimensional, spherical. This is also known as a space fill diagram. Okay, this particular diagram is also known as a space fill diagram. But over here, do you see we haven't filled the entire space? Over here, we've filled the entire space. Why are we filling the entire space? Because we are visualizing our ions as spheres. We can, right? Because there's a spherical distribution of electrons around the nucleus, right? So we can imagine our atoms as spheres to a very good extent. So that's why we've put spheres over here, right next to each other. Space fill diagram. This one, on the other hand, can be called the ball and stick diagram. Okay. Fine. So this one is known as a ball and stick diagram. Over here, we've replaced the space fill. We haven't filled the space. We've zoomed in even further and we've distributed it in the sense of points connected with a stick. Okay. Fine. Okay. So can you see? These are basically the points where you have sodium. Okay. These are all the points where you have sodium. Right. On the other hand, these are all the points where you have chlorine. Okay. So when I'm depicting the crystal arrangement with points, crystal lattice. These particular points, my dear friends, where these constituent particles are present, these points are known as lattice points. Lattice points are those positions in a crystal lattice where the constituent particles, in this case ions, of the solid are present. Fine. These are your lattice points. Now that we've understood the lattice, let us come to the main question of today's class. What is a unit cell? My dear friends, before I explain to you and show what the unit cell is, let me ask you a question. Okay? The question is very simple. The question is, what is wavelength? Once we answer this question correctly, we'll be able to understand the unit cell in a much easier way. Fine. What is a wavelength, people? How do you define wavelength? Yes, I'm talking about waves. Yeah? Waves chapter. I'm sure you studied it in 11th class physics also. You've studied about wavelength in earlier classes, I'm sure. So let's take this type of a wave. Sine wave, right? This is known as a sine wave. Sine x ka function hai ye. Everyone knows that, I'm sure. So, a lot of you would be saying right now that, sir, a wavelength is basically the distance between two consecutive troughs. Sorry, two consecutive crests in this case, or two consecutive troughs, right? This is what most of you would be saying right now. It's the distance between two consecutive crests or two consecutive troughs. My dear friends, this definition is okay, but since you're learning with Mr. Pahul PSG, we need to understand it in a better manner. Okay? Tell me one thing. If I take this point and this point, can I say the distance between these points is a wavelength? I'm sure you'll be like, yeah, we can. Yeah, we're starting from the half of the wave to the next half of the wave over here. Fine. Okay. Again, let me take this particular point, this random point over here. This is not a crest, this is not a trough, this is not the midpoint, nothing. Okay. Let's take the same point again. Yeah. Do you realize these 2 points are basically twin brothers, twin sisters of each other, right? Do you realize that this is also a wavelength? Can you see? This is also equal to the distance between two crests or two troughs. And the same thing applies over here. This is equal to the distance between two troughs or two crests. Yeah? So I can say that these are wavelengths. Now, how do I define this? Some of you must be thinking, okay, we can define it like the shortest distance between two consecutive similar points of the wave. That if I have two similar points of the wave, the shortest distance between them, yeah, I don't want to take it from here to here. That won't be the wavelength. That will be too long. That will be double the wavelength. Yeah. So the shortest distance between two similar points on the wave is my wavelength. That is also good. But let me give you an even better definition. I'll write it down and you also write it down with me in your notebooks. The wavelength is the shortest part of the wave. The wavelength is basically the shortest part of the wave that can be replicated in either direction that can be replicated in either direction to create the entire wave again. I know. My handwriting. Looking at my handwriting, a lot of people say that I should have been a doctor. But yeah, here I am teaching chemistry. So, wavelength is the shortest part of the wave that can be replicated in either direction to create the entire wave again. Let me show you what I mean by this. Okay? If I take, people, this part of the wave. Okay? If I take this part of the wave, yeah, this is the part that I've marked out. Can I copy and paste it again and again to create the entire wave in both directions? Copy, Control C, Control V. Copy, paste. Do you see what I mean to say over here? Copy, paste. Again, paste it over here. Whatever. Get the point? Similarly, I can do the same thing with this particular wavelength that I've marked out. Yeah, all of the lengths are the same. Fine. The points marked out are a little different. But this is what I have over here. Yeah, approximately. Copy, paste. Copy, paste. I'm making these gaps to make it clear. Okay. Copy, paste. Do you see that using this particular part, I can copy paste it in both directions, either direction, to recreate the wave? Do you realize that this is a much more inclusive definition of the wavelength? Isn't it? It includes all possible cases and it gives you a much better idea of what the wavelength is. It's just the shortest part of the wave that can be repeated. Can this be the wavelength? From here to here, can you have the wavelength? No. If I repeat this in either direction, I'm not getting the wave, right? I'm getting something weird. Fine. So the shortest part of the wave that can be replicated in either direction to create the entire wave is the wavelength. Please make sure you write it down. Note this visualization as well. Now, my dear friends, I will give you a definition of the unit cell and you'll be like, what is a unit cell? Unit cell is the smallest portion of a crystal lattice which, when repeated in all directions, generates the entire lattice. See, wave, we drew it in 2 dimensions. We drew it on the plane of this particular blackboard. Lattice exists in 3D. So basically, for replicating the wave once again, you had to replicate the wavelength in these 2 dimensions. Right? Getting the idea? Or 1 dimension, but you get the point. Now over here, for creating the entire 3D lattice, we have to replicate the unit cell in 3 dimensions. That's the only difference. Otherwise, the point of the unit cell is basically the same. We take the entire lattice And out of that, we recognize the smallest part that is repeating in all directions. And that part is known as the unit cell. This is the definition. I'll show you an image and the things now will be crystal clear, I'm sure. Unit cell is the smallest portion of a crystal lattice which, when repeated in all directions, generates the entire lattice. Exactly the definition of wavelength that we give, right? This is the entire lattice depicted by points. Now out of that, if I take out the smallest segment that I can repeat again and again and again, can you see that this cube that we've made over here, yeah, I'll highlight it with my pen also. Oh, my drawing skills are so pathetic. Yeah, so this is a random arrangement that I have made over here. Fine. So can you see that this red part, at its corners, my particles of the solid are present. And if I replicate this particular cube in this direction, in that direction, front, upward, downward, I am basically creating the entire lattice. Right? I just need to copy paste this in 3 dimensions. So my dear friends, what we've learned till now, crystal lattice is the entire structure of the solid in 3 dimensions. If the wall of the house, let's say, is the entire lattice, then your unit cell or the smallest unit is basically a brick. Nice way to keep it in your mind. Okay, so this is a representation of a certain unit cell in 3 dimensions. Fine. Write this down. If you can draw this image in your notebook, perfect. If you can't, then don't worry, for today's class I'll give you the PDF. Perfect. Chalo. Now this is 3-dimensional, but for 2 dimensions I have some exercises, okay, some very fun exercises that you have to do with me. Okay, I'll do them for you. You just enjoy the visual delight. Okay, so over here, imagine that this is just a 2-dimensional lattice, nothing coming out of the plane of the board. Okay, so 2-dimensional lattice. My dear friends, can you recognize the unit cell? It's already been drawn over here, that this rectangle with the lattice points at its corners is my unit cell, because I can basically replicate this rectangle again and again. Okay, this rectangle, can you identify this rectangle again and again? Now this is another way to think it, because what I said is unit cell can be replicated to create the entire crystal, but in nature crystals are already created, right? I am not creating the crystals. So in nature what you have to do is you see a crystal and then you have to recognize the unit cell that is repeating again and again. You have to recognize the smallest repeating unit. Just a top-down approach now. Earlier it was a bottom-up approach. We took a unit cell, we imagined that we are creating the entire lattice out of it, but now we realize we are in nature, we are in this universe. All the crystals are already created. I am not taking a unit cell and creating any crystal. So what we have to do actually is observe a crystal that exists in nature already and try to see what is the smallest repeating unit, and that is the unit cell. So what's the smallest repeating unit over here in this 2-dimensional lattice that's already created? This particular rectangle with corners as lattice points. Fine. So over here it's like a rectangular unit cell. Okay, cool. This one, again the unit cell is made over here, so you get the idea. In this 2-dimensional representation, this particular rhombus, again with its corners as lattice points. Basically, at its corners, you have the presence of the constituent particles of the solid. Maybe ions, maybe atoms, whatever. Fine. So if I keep repeating this rhombus, I basically get the entire crystal lattice. This rhombus is the smallest repeating unit inside this particular Okay? So now the thing is that a lot of students might be thinking, sir, can't we have triangles? Sir, can't we have triangles? A lot of you are able to see this triangle as well, I'm sure. Now the problem with triangles is that, see, what I'm doing is, I am making this triangle, I made this triangle, I made this triangle, I made this triangle, I made this triangle. Do you see there is a gap over here? First of all, this gap is a problem. Second of all, if I just, if I am a scientist, I did the research on a crystal and I have to pass the information to you, and I don't have enough space in my hard drive to pass on the entire crystal. So I will pass on the information of only the unit cell. I'll say, okay, this triangle is the unit cell. Now when you're replicating the triangle, how do you know how to replicate it? I said replicate it in 3 dimensions. How? You can start representing the, replicating the triangle like this maybe. This is wrong. Yeah, do you see, this gives a totally different arrangement. So what point of the triangle do I balance? Then it also creates these gaps. Okay? So we don't consider these triangles to be unit cells. In the case of, let's say, something that has 4 sides, it's very simple how to replicate it. If I have to replicate this guy, obviously over here, sharing one side with this, I can make another one. On the top as well, sharing one side with this, I can create another one. Sharing of these edges is very important. It's like we're cutting a cake. When you cut a cake, whatever cuts you've made, the edges are still shared, right? In a pizza, when you cut the pizza, the edges are still shared by all the pieces, right? So over here, can you see? All the edges are shared by all the unit cells. Fine? All the edges are shared by all the points. That is very important when you're creating the smallest, or when you're looking for the smallest repeating unit. Fine? Also, one more thing is that the smallest repeating unit could be created from any of these points. No matter where I have a point in the lattice, if I start with this lattice point, I should be able to create a unit cell from this point. Take any random point, okay, this one, I'm able to create a unit cell, perfect. In fact, I'm able to create multiple unit cells. Yeah, starting with this particular point. So, no matter where you start, okay, no matter what lattice point you start with, you should be able to create a unit cell. Because of symmetry. Crystal arrangement in space is symmetric. If it's not symmetric, it will become amorphous, right? Yeah. Crystalline arrangements have a very beautiful arrangement, a very beautiful symmetry in them. So because of that symmetry, the smallest repeating unit can start from any of these lattice points, and all of it looks basically the same. Yeah. All of these rhombuses are the unit cell. Just some intricate points about the unit cell that no one really cares to spend time on, but it's useful. Okay, let's see some more arrangements. Ye dekho. This is a very nice arrangement, by the way. What is the smallest repeating unit that you can recognize over here? Yeah, what's the repeating unit over here? Again, something like a rhombus. Yes, this particular rhombus, no matter where I am, no matter what lattice point I start with, I can create that rhombus. Some of you, instead of recognizing a rhombus, would have recognized a hexagon. Yeah, I'm sure a lot of you have recognized this hexagon over here, where the lattice points are not only the corners, but there is a lattice point in the middle of the hexagon also. That can be called a lattice point. You can say that, okay, it's the middle of the hexagon is also a lattice point. Fine. And I'm sure you can see that this can also be replicated again and again. Yeah. And I'm sure a lot of you can see that this can also be created from any lattice point. This one, you're saying, sir, but this is trapped inside the hexagon. How can I create another hexagon from here? Create this hexagon. Yeah. So this hexagon is also a repeating unit. I can also create this hexagon from any lattice point. All hexagons look the same, don't they? But the problem over here, my dear friends, is that this is not the smallest repeating unit. This is a repeating unit, absolutely fine. But this is not the smallest repeating unit, and therefore it is not the unit cell. Smallest repeating unit is the unit cell. So what's the smallest repeating unit over here? This good old rhombus. Now just to name it, just for the name of it, you can call it a hexagonal two-dimensional distribution. You can give it a name of hexagonal distribution, but you as a smart scientist have to understand that still the repeating unit is a rhombus. You might call it hexagon just to sound fancy, but the repeating unit is still a rhombus kind of a thing. Okay? Now why am I telling you all of this? It will be very important when you come to the actual 3D unit cells. कोई ना आएंगे उस पे. This arrangement, can you find out the unit cell? This one's very nice. I like this. Can you figure out what's the smallest arrangement that can be replicated again and again? I am sure a lot of you are seeing this particular square. So the lattice points are the corners of the square, and then one lattice point in the middle of the square. But do you see that I can't replicate it? Now I have empty squares, one square with one centered lattice point, then empty squares, then one center wala, then one empty wala. So I'm not able to replicate it in all directions. This is not my lattice, unit cell. Okay, so what could be the unit cell? What could be the smallest repeating unit over here? Does this make sense? Yeah? What do you think? Can you see this? So the lattice points are present at the corners of this particular square. It's just a tilted square, right? So the lattice points are present at the corners of this square and also on the edge centers of this square. Yeah? The lattice points are also present at the edges of the square. I'm using normal English. Edge, corner, everyone knows that, right? So don't get confused. Yeah, over here there would also be. You can start replicating the entire lattice in all these directions with this unit cell. Make sense? Fine. Got it. Chalo. Another representation over here. Again, similar to that hexagonal case that we saw. I'm sure a lot of you are seeing these hexagons. Yeah. Hexagons present everywhere. Fine. But again, is it the smallest repeating unit? The smallest repeating unit again is this tiny little diamond kind of a thing. Basically this, whether it's a rhombus or a square now depends on the exact measurements, but you get the idea that this is the smallest repeating unit. Fine. Okay. Chalo ji. So we properly understand what's a unit cell. It's the smallest repeating unit of a crystal lattice. Simplified. Much more simplified. Now let's come back to the three-dimensional unit cell. We saw all sorts of 2D unit cells. Some were square, some were rectangle, some were rhombus, some were diamond, etc, etc. But now in 3 dimensions, we have more parameters that we can change. Imagine that this is a 3-dimensional unit cell. Now in this 3-dimensional unit cell, what are the parameters that we can change? What are the cell parameters that we can change? We can basically change the lengths, right? This is a length, this is a length, this is a length, okay? Can you see 3 different lengths? Fine. So if I change the length of this particular unit cell, if I change the length of this particular, this particular side of the unit cell, this particular side of the unit cell. So basically what I'm trying to say is that in nature, different crystalline arrangements are possible. And in those different crystalline arrangements, you will have different types of unit cells. What will those unit cells look like? All unit cells will have different shapes. How will their shapes be different? Their shapes will vary in terms of either the angle or the length. For example, in the two-dimensional cases, we saw a unit cell that looks like this. Yeah, we also saw a unit cell that looks like this. Right? We also saw a unit cell that looks like this. Fine. What is different about each of these? Over here, the angles are 90 degree. Yeah. Over here, one length is long, one length is small. Over here, both the lengths are same. Over here also both the lengths are same, but the angle is not 90 degree. It is an obtuse angle. Right? This angle is not 90 degree. It is an acute angle. So do you see that in these different unit cells, how do they differ from each other? Lengths, angles. So the same thing when we replicate in 3D, this is what we get. And these lengths and angles are known as my unit cell parameters. No rocket science. Okay, fine. So let's call one of the length A, one of the lengths B, one of the lengths C. 3 edges in 3 dimensions. So 3 lengths. Okay. So A, B and C are called edge lengths. Please write this down. I'm giving you a nice detailed idea of the unit cell. Similarly, there are these angles. Okay. This is an angle. Let's call it alpha. This is an angle. Let's call it beta. This is an angle. Let's call it gamma. Basically, all the angles between these planes. This is a plane, this is a plane, this is a plane. So angles between these respective planes. So we've got alpha, we've got beta, and we've got gamma. And these angles are basically known as interfacial angles. Okay? Interfacial angles. Basically, this is a face. This is a face of the unit cell. Basically a rectangle over here. Yeah. This is a face of the rectangle. This is a face of the rectangle. So the angle between these two faces is beta. Interfacial angle. Fine. You can also call it an interplanar angle, by the way. Angle between two planes. So ABC are called edge lengths. Alpha, beta, gamma are called interfacial angles, sometimes called interplanar angles. Fine. Now, with the variation of all of these, we can form these 7 different types of 3-dimensional figures, for the lack of better words. Okay? Okay. So in 2D, from square we got rectangle, and rectangle, then we had rhomboid, rhombus, parallelogram, etc., etc. You know all those 2-dimensional figures, right? Rhomboid is 3-dimensional, I'm sorry. But the same thing over here, you start with a cube, then you yeah, extend one particular side, becomes sort of like a 3D rectangle, yeah, etc., etc. So now, my dear friends, these particular drawings that are there, you can try to make them in your notebooks. Okay, you can try to make them in your notebooks, and they're given in the NCERT. I have taken these images from the NCERT. So now let's try to understand, looking at these images, what are their cell parameters? Fine. Over here, my dear friends, this is a cubic type of unit cell. Depends on the crystal arrangement. When we looked at the crystal arrangements repeating unit, we found that it is a cubic repeating unit. Okay, fine. So now this cubic repeating unit, what are the properties of it? Can you see that all the edge lengths are the same? What is the edge length, sir? Depends on the crystal. When we take real life examples, we'll see. Yeah. But for now, if there is a cubic unit cell out of a certain crystal lattice, in that cubic cell, the properties of that cubic cell are A equal to B equal to C. All the edge lengths are equal, and all the angles alpha, beta and gamma are equal to each other and equal to 90 degrees. I'm teaching you what 8th class, 7th class geometry. How do you define a cube? This is how I define a cube. Right? ठीक है जी. Fine. Now let's come to tetragonal. How is tetragonal different from this? Just one side is elongated. You basically made a three-dimensional rectangle. Only one side is elongated. One side is still a square. Okay? Fine. So what's happening over here? A is equal to B, but is not equal to C. C is longer, A and B are equal. Okay? One base is square, but the length is longer or shorter. Could be shorter also. Could be like this. Sorry, my drawing is very nice. Yeah. Could be like this. This kind of a three-dimensional structure. Getting the idea? So the height is small, but the base is longer. Okay, that can also be the case. So A is equal to B, but not equal to C. Angles are still equal to 90 degrees. So in your notebooks, if you're not able to make the diagrams, at least write this. Cubic unit cell, what are the properties of the parameters? Tetragonal unit cell, what are the properties? So on and so forth. Okay. Orthorhombic. I'm sure we can see the image and write things down. A is not equal to B is not equal to C. Okay. A is not equal to B. A is not equal to C. What about the angles? Look at the image and tell me. It's written. Angles are 90 degree, okay? So alpha is equal to beta is equal to gamma is equal to 90 degree. So in these first three cases, my angles are at least 90 degrees. Okay? They are just weird three-dimensional versions of a cube. Please write it down. This box, can you see? This is like an orthorhombic box. Fine. The base is different. The sides are of a different length. It keeps lying here in the studio. This is a makeup box for people who want to brush themselves up before the classes. We have lady teachers as well, of course. Right? So just this part, can you see? Yeah. Base, height, all three lengths are different. This length is different from this length, is different from this length. So this is basically your orthorhombic kind of a three-dimensional structure. Last one, hexagonal. Hexagonal. This is why I told you the hexagonal case in 2 dimensions also, because if I just showed you in 3 dimensions, it becomes a little difficult for students to understand. I've taught solid state multiple times now to students, and I've realized that I need to show this in 2 dimensions before I come to 3D so that students can understand it better. Fine. So over here, I can make a hexagon, but it's not the smallest repeating unit. My smallest repeating unit is basically a rhombus type of a structure. Yes. I've just made that rhombus into a 3-dimensional shape. Yeah, can you see? Fine. You can make a hexagon. That hexagon will also be repeating, but it will not be the smallest repeating unit. Smallest repeating unit is a rhombus. So over here, what are the properties of this 3D rhombus? Hexagonal arrangement. The properties of this 3D rhombus are that in the base, the 2 sides are the same. In a hexagon, it has to be a symmetrical hexagon. Okay, fine. That's how this arrangement is defined. A equal to B, but not equal to C. It is very tall. Can be very short also. Okay. And the interesting thing is that 2 of the angles are 90 degree. 2 of the angles are 90 degree. Basically, my dear friends, what's happening is that this particular angle, okay, this particular angle, this is 120 degree. Okay. Otherwise, do you see it's just stretched out at the top. So the angle from the base of this height will be 90 degrees only, right? Yeah. Getting the idea? This angle is 90 degree. Okay. Fine. This angle is 90 degree. That is not changing. But this angle is 120 degrees. Okay, so basically the point is that one of these angles, okay, which is called gamma over here, is equal to 120 degrees. One of the interplanar angles over here is 120 degrees. That's the point. That's the main point over here. Cool. Other interplanar angles, base to this height, base to this height, 90 degree angles. Okay, so this is the main point that you need to remember over here. Fine. If you want to take a screenshot, do that. Then I'll move to the next page. 3 more three-dimensional structures of unit cell. Rhombohedral. So in a rhombus, what's the main property? That in the rhombus angles are different, but the sides are the same. Same thing in this 3D rhombus, rhombohedral. So what's happening over here is A equal to B equal to C. Fine. Angle में क्या चल रहा है? Alpha is equal to beta is equal to gamma, but this is not equal to 90 degree. The angles are equal. The angles are also equal. It's a nice symmetrical rhombus. But the thing is that these are not 90 degree angles. These are some obtuse angles. So you're saying, sir, why didn't we consider this acute angle? Because if we fix the obtuse angles, this acute angle will automatically get formed, right? That is why. So don't worry about this. Okay? So, rhombohedral distribution of the unit cell. Now we come to the monoclinic unit cell. This is interesting. Okay? This is interesting. So what's happening in the monoclinic case? A is not equal to B, is not equal to C. Two of the angles are 90 degree. Okay? Alpha equal to beta equal to 90 degree. Over here it says gamma, you can call it beta if you want. And your gamma is not equal to 90 degree. Basically, one of the angles is not 90 degree, two of the angles are 90 degree. Okay? Very weird three-dimensional shape. Teda sa hai. Can you see that this is a nice rectangle over here? Huh? This is a nice rectangle over here, but now the rectangle is stretched in 3D in a weird slanted teda sa angle. Okay? Triclinic. Easiest to remember. Maybe not the easiest. Cubic is easiest to remember. But in triclinic, A is not equal to B, is not equal to C. Can be anything. And alpha is not equal to beta, is not equal to gamma. Ajeeb. Triclinic. Fine. Chalo ji, aage badhte hain. Let's move ahead. Now, in these different unit cells, where can my atoms be present? Where can my lattice points be inside these different unit cells? Basically, all the unit cells were teda-meda versions of the cube, right? For example, in the 2D unit cells, all the 2D unit cells were teda-meda versions of the square. Long square, short square, teda square. We call them different names. Similarly, in the 3 dimensions, all the unit cells that I have are basically the different types of cubes. Long cube, short cube, different angle cube, etc. But for easier understanding. Now, what are the points of atom placement or ion placement, depending on what kind of solid I have? What are the points of placement of different atoms or ions inside those unit cells? One is very simple. One is very simple, that when the constituent particles are present only on the corner positions. Okay? So there can be a crystal lattice in which the constituent particles are present only at the corner positions, and those particular cells will be called primitive unit cells. Fine. When the constituent particles are present only at the corners. I'll show you the image of these, don't worry. For now, write the definition. And then you have centered unit cells. In centered unit cells, you have atoms at the corners. Atoms will be there at the corners all the time. Okay. No matter what unit cell you have, no matter what crystal lattice it is, atoms will be there at corners. Because in 3D, when you go to find the smallest repeating unit, in that, atoms will be there at the corners. Like we saw in the case of two-dimensional unit cells, right? In all the two-dimensional cases that we saw, there were atoms at the corners. In one case, there were atoms at the edges, but still atoms at corners were there, right? So, centered unit cells are basically those where apart from the corners, unit cell contains one or more constituent particles present at positions other than corners. Yeah, can't be simpler than that, no? So centered unit cells are basically at corners and some other points as well. Okay, so in centered unit cells, basically we have three different kinds. One is called the face centered. Another is called the body centered. And we have another one called the end centered. Okay? We might have special cases where there are edge centered, but we'll understand where they happen. We won't count them as centered unit cells over here. Edge centered, we'll think about that later. But centered unit cells are of three types: face centered, body centered, and end centered. What are these? I'll show you now. Okay, so if you want to write these definitions, you can pause the video over here and write them. First case, simple cubic. Atoms are present at corners only. Can you see? Simple cube. For the sake of simplicity, we have taken cubic unit cells over here. You could have a rhombohedral unit cell. You could have a triclinic unit cell with atoms at corners. But for simplicity, we've just shown cubic. Okay. So simple cubic, atoms or ions are present at corners only. Ball and stick diagram, space fill diagram. And in this space fill, what we've done is we've basically imaginarily cut it into a nice cube. So in the space fill, with our imagination, we are not actually cutting into atoms. Okay, imaginarily, we've basically just cut this into a nice little cube. So whatever is hanging outside the cube, can you see this part is hanging outside the cube? So we've basically not included it. Yeah, this was the part hanging outside the cube. Okay, so we've just ignored it. So this is what the space fill of a unit cell looks like. This is basically the space fill diagram of a unit cell. By the way, no matter who you go to apart from me for chemistry on YouTube, till now, maybe after me, some people do this, but till now, no one will tell you about these names. Okay, no one will go into so much detail. There's a ball stick model. No one goes into so much detail. Why? Because to most teachers, or to most people, I should say, or to most students also, the only thing that's important is marks in their examinations. For me, science is important. I am teaching you science because I love to teach science. Because I want you to enjoy science. I'm not teaching for you to just get marks. If you enjoy science, you'll automatically solve a lot of questions, which will automatically build a lot of skill for your examination. Space fill of a unit cell when we cut out the excess. Cool. Simple cubic, atoms are present at corners only. I'll show you even more beautiful representations, by the way, don't worry. Body centered. Atoms or ions are present at corners plus body center. At corners, and can you see there's one at the center also? Yeah. Can you see this guy is present at the center? This lattice point is at the center of the entire cube. Can you see it is enclosed over here inside? Yeah. Can you see there's one entire sphere inside this, surrounded by the corners? So this is the body centered case. Okay, these diagrams are made in the NCERT, by the way. Same diagrams will be there in the NCERT, so don't need to worry too much about it. Face-centered. Atoms are present at corners and face centers. Basically, what is a face? This is a face. This is a face. This is a face. So when you have an atom present at the center of the face, you call it face-centered. Okay? Can you see? At the corners, atoms are present, but I'll show you the face-centered ones. This is present at that particular face. At the front face, you have this guy. At the top face, you have this guy. At this particular face that is pointing towards me, I have this guy. At the bottom face, I have this guy. At the face right at the back, we have this guy. Fine. So I've marked all the face-centered atoms. How many face-centered atoms are there? 6. Yeah, 6 faces. So 6 face centers. Fine. This is the space-fill diagram. This is the space-fill diagram. This is the cube. Okay. So space-fill diagram, when you cut it, removing the excess, can you see a very nice image is made over here? So looks so pretty. These are the face centers. कितना सुंदर दिख रहा है. Looks so beautiful over here. Fine. Face centered. End centered is a case where atoms ions are present at corners and only at 2 opposite faces. So face centered when they are present at all 6 faces. End centered is the case where they are present only at 2 faces, 1 and 2. Depending on the crystal, could be either of the 2 faces. Fine. End centered. End centered is not very common, by the way, and in our analysis of the rest of the syllabus, we'll hardly ever see end centered, but it's important to understand what end centered actually is. Now, my dear friends, since you are studying with Mr. Pahul PSG, I have better visualizations for you. So a shout out to this particular website, by the way, ibiblio.org. This is the web page. You can search for it on Google and visit this. Fine. I'll give a link of this in the pinned comment of the video, so don't worry. So they have very beautiful 3D models of these lattices. I'm sorry the page suddenly turned white, so you might be blinded by it, but just have a look. Simple cubic. Simple cubic unit cell, primitive unit cell. Primitive unit cell can also be called simple cubic. Can you see? Atoms are present only at corners. Nice, right? This is a ball stick model. Balls are a little bigger, but yeah. Ball stick model. Nice 3-dimensional visualization. बताओ और कौन दिखाएगा? Who else will show you? Nice, right? Let's see the body-centered case now. This is the body-centered type of unit cell. At corners, and one guy is trapped in the center. Can you see? That's trapped in the center. Body-centered. Atoms at all corners and one atom at the center of the unit cell. Very nice. As I told you, this is the most visually entertaining chapter of chemistry. Face-centered cubic. Face-centered. Can you see what's happening? At all corners and at all faces. Yeah? Can you see this present at the face? This is present at the face. I'm pretty sure you can very beautifully see the faces over here. Can you see this face-centered? This face-centered. This face-centered. Yeah? Beautiful visualizations, people. This gives you a very nice idea of what these unit cells look like. Perfect. Perfect, perfect. Chalo ji, come back to the slideshow. So unit cells are clear. Types of unit cells are clear. Different types of these arrangements, these lattice points arrangements are clear. What are the 4 lattice points arrangements? you have simple cubic, which is the primitive case, and then 3 centered cases. So 1 primitive and 3 centered cases: body centered, face centered, and end centered. Cool. Yeah. So now, my dear friends, what is the total number of combinations possible? What are the total number of combinations that are possible? In the sense that we had 7 different types of unit cells. 7 different types of those cubic 3-dimensional shapes. Cubic, rhombohedral, orthorhombic, triclinic, monoclinic, hexagonal, so on and so forth. Yeah, you had 7 of those. And multiply these 7 unit cells into the different types of lattice point arrangements. 4 different types of lattice point arrangements. Simple, only at corners. Then you have body centered, face centered, end centered. 4 of these arrangements. So what are the total kinds of lattices possible? Total kinds of lattices possible are basically equal to 28. 28 different kinds of unit cells. 7 into 4. 7 are basically the geometrical shapes. 4 are basically the lattice point arrangements. So total 28. But my dear friends, these 28 don't exist. Only 14 exist in reality. Only 14 different types of crystal lattices exist in reality. Only 14 of these combinations actually exist. The remaining 14 don't exist. Why? Only 14 of these combinations exist. If you read the NCERT, these 14 combinations are called Bakwaas lattices, named after the scientist. Okay, so these 14 Bakwaas lattices are the only arrangements that exist. I'll show you, I'll tell you what are the ones that exist, but 14 of them do not exist. Theoretically possible, but practically they don't exist. Why? See, a lot of times, a lot of other teachers will just tell you that they'll start the class over here. That bacha 14 Bakwaas lattices exist. Why? No one knows. Let me try to explain it to you. See, Bakwaas lattice is this idea, and the analysis of it is very mathematical. Okay, it's extremely mathematical. If you try to open the Wikipedia article of Bakwaas lattices, you'll be blown away. I'll give you a very simplified idea. Do you realize that a crystalline arrangement needs to be symmetrical in nature? Point number one. Okay, and this idea, you don't have to understand it. It's not compulsory for you to understand why. It's not a part of your syllabus. No one will ask you. It's a little advanced. It's a little tricky a concept. So I'm telling you for the sake of science. If you want to listen to it, great. If you don't want to listen to it, just skip through this part. Okay. So why only 14 Bakwaas lattices exist? See, the idea is a little tricky, but the basic premise behind that idea is that a crystal lattice has to be symmetric, and therefore the unit cell has to be symmetric. Symmetric in the sense that it should be repeatable in all directions, right? Right? We saw why the triangular case can't be the unit cell, because its repetition in all directions is not well justified, not well defined, right? Isn't it? So, point number one is, in a lattice, in a unit cell, we need symmetry. Perfect. The second point, my dear friends, is that the unit cell should be creatable. You should be able to find a unit cell from any lattice point. Remember, I showed you that case in 2D also. That if I start with any lattice point, I'm able to create a unit cell, any lattice point, unit cell, any lattice point, unit cell. So, basically what's happening in the 14 cases that exist is that you are getting a symmetry also. Fine. Overall symmetry is there, and from any lattice point you can create that particular unit cell in 3 dimensions. But the 14 Bravais lattices that don't exist, they don't satisfy this particular property. Okay, in the 14 Bravais lattices that don't exist, basically you can't create an entire lattice. You can't find a unit cell from every lattice point. Okay, so the 14 Bravais lattices that do not exist in reality, basically they don't meet this criteria. That if you pick up any lattice point and try to create a unit cell from there, not possible because of asymmetry. So if you study the higher level idea, the maths behind it is very complicated, but it's called the translational property of Bravais lattices. Okay, it's called translational symmetry. Basically, it interprets to that I can start from this lattice point and create the unit cell. I can start from this lattice point, create the same unit cell. Start from this lattice point, create the entire same unit cell. Okay, so only in 40 Bravais lattice that is possible, 14 of them. In the other 14, this property does not exist. And that is why they are not present in nature either. Fine. So, if you enjoyed that part, cool. If you skipped through it, then okay, fine. So, finally, this is the summary of what we've studied till now. Okay, this is the summary of what we've studied till now. Till now, we have understood that there are cubic, tetragonal, orthorhombic, hexagonal, rhombohedral or trigonal, same thing, monoclinic and triclinic, kind of 3-dimensional shapes. In those 3-dimensional shapes, we possibly can have simple cubic arrangement, body-centered arrangement, face-centered arrangement, and end-centered arrangement. But 14 of those are possible because of symmetry. 14 of those are not possible because they don't have the translational symmetry. Because these 14 of those that don't exist, that unit cell can't be created from all lattice points. Okay? So these are the ones that are possible. Okay? Cubic mein, in a cubic unit cell, primitive is possible, body centered is possible, face centered is possible. Tetragonal mein, primitive is possible, body centered is possible. Orthorhombic mein, primitive, body centered, face centered, end centered, all of them are possible. Okay? Hexagonal, only primitive. Rhombohedral, only primitive. Monoclinic, primitive and end centered. Triclinic, only primitive. Do you have to remember this? I have never seen anyone ask about this in an examination. Okay, never have I seen anyone ask about this in an exam. So read it, count them, they'll come up to be 14. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14. Fine, just have fun with them. But basically, no need to worry too much about them. Okay, these are properties that we studied. Then examples are given. In some cases, NEET and JEE Main can ask, okay, very simple questions that zinc oxide, what kind of crystal system does it belong to? So you then need to remember that it is hexagonal. Okay, very rare cases. I know it's a purely memory based kind of question and it should not be asked if you ask me, because who's going to remember so much detail, man? Detail that you can easily look up on the internet. But sometimes, especially in NEET exams, they can ask such questions. So just have a look at the examples, write them down in a notebook. This table is again taken from the NCERT. So no need to fret too much about it, but yeah. Nice. Very nice. ठीक है जी? चलो. So now let's do this and then we'll solve some questions. So it seems like this class will be of the duration of somewhere around an hour and a half, 1 hour 30 minutes approximately. But you can always watch it on YouTube at a faster speed. So I'm sure you guys are more efficient at watching the class. So I will make an exception over here today and take a 1.5 hour class, although I don't want to extend it more than 1 hour, but today I'm sure you're having fun. Chalo ji, contributions of individual lattice points. Now, the thing is that different lattice points, we've understood corners are a lattice point, body center is a lattice point, face center is a lattice point, end centered could be cases of, unit cells where only two faces are occupied. So the point is that what is the contribution of the atom inside the unit cell of these individual points? See, you remember these images? Basically, my dear friends, this idea of a unit cell is imaginary. Nature doesn't think about unit cell, it just creates a crystal. The crystal is created because that's how things are stable, right? Anything that exists in nature in a way that it does is because it is stable. Fine. So crystals are stable in that arrangement. Now to understand that arrangement, we have tried to zoom into them and then try to find a repeating pattern. And then if we find a repeating pattern, we're like, oh, if I can just understand this small unit, I can understand the entire lattice. So that's just a human pursuit. So all of this analysis is just a human pursuit of understanding the solid state. So don't imagine that, oh, sir, how can nature cut atoms into two? This is just our imagination. So in the space-fill scheme of things, this is what my unit cell looks like. Fine. Inside this unit cell, can you see at the corners, the entire atom is not present inside the unit cell. Only a small fragment of it is present. Even at the face centers, can you see half of it is cut off? So only half of my face center lies inside the unit cell. Cool. I have a bad mustache day, it seems. So I have to adjust it again and again. Yeah. So only half of the face centered atom exists inside the unit cell. Because it's our imagination, this is how we define the unit cell. Okay. Again, if you repeat this unit, you will create the lattice once again. Okay. If you want to do that, you can try to draw it if you want. We'll do that later. But the point is that this is unit cell. You can replicate it in all the directions. And then, let's say you replicate it in, I'll show you what I mean. If you replicate it in this particular direction, let's say, fine. So now the other half of the face centered will come inside this. Yeah. So you've created the entire atom by replicating it in this side. Fine. Getting the idea? So this is just imaginary. Smallest replicatable unit. We are trying to observe the pattern. Cool. So now let us try to see what are the contributions of individual lattice points. So my dear friends, if my atom is present at the corner of a unit cell, okay? If my atom is present at the corner of a unit cell, this is the ball stick figure, this is the space fill figure. There are 8 corners in a cube, fine. Each atom at the corner is shared among 8 unit cells. See this diagram over here. This is one unit cell. Okay, this particular thing is one unit cell. Fine. Now can you see there are 8 unit cells, 1, 2, 3, 4, 4 at the top, 4 at the bottom. Now this particular atom is essentially present at the corners of all of these unit cells. Can you see that this particular atom, a sphere, is shared equally among all of these 8 unit cells at the corner, right? Each atom at the corner is shared among 8 unit cells. So its contribution to just one unit cell is 1 by 8. As simple as that. ठीक है? So for the corner atom, okay, contribution, this is what you have to write in your notebook. 1/8. Okay. If in a unit cell an atom is present at the corner, it contributes only to 1/8 inside that unit cell. Fine. Rest of it is present in other unit cells. Unit cell, again, as I said, is the smallest replicatable part of the lattice. which we humans are able to observe. It's imaginary, therefore we can cut it wherever we want. That's why we're cutting the atom also. Okay, so contribution of the corner atom is 1/8. Very simple. Now let's move on to the, as a corner atom, this is also an imagination. Okay, this is also a visualization, by the way. You can see 8 unit cells. One of them is already highlighted. So if you notice this guy, it is shared between 8 unit cells. 1, 2, 3, 4, 5, 6, 7, 8. 4 at the top, 4 at the bottom. 1/8. Chalo. Face center. By the way, people, once again, read the NCERT of this chapter after my class. I will give that to you as your assignment as well, so that you understand this chapter better. My teaching plus your reading of the NCERT equals to crystal clear concept. And I dive a lot into the details. I like to throw you into the deep end so you can understand how to swim on your own. That's my style of teaching. Yeah. So I am not a spoon feeder, as I've always said. And therefore, I try to push your limits as much as possible so that your brain can evolve. Face center. So, ball stick model. Just look at this beautiful space fill model that we've shown over here. Face center. It's very easy to see, people, that only half of the sphere is inside the face, right? Half of the sphere is cut. So there are 6 faces in a cube. Each face is shared between 2 unit cells. So its contribution to 1 unit cell is half. If you want to see that image again, that animation again, yeah, face centered. Can you see? Look at this particular sphere. Half of it is inside this unit cell, half of it is outside the unit cell, cut off. Can you see how half of it is inside, half of it is outside? Face centered. Corner, maybe you can see 1/8 of it is inside, the rest is outside. Fine. Very beautiful visualizations. So face centered, the contribution is 1/2. And we'll solve questions, by the way, in some time so that we can, use these numbers properly. Once we use these numbers, they'll fit better into our brain. So face center contribution is half. Body center, the entire atom is present inside the body center. So of course the contribution of the body center is 1 entire atom. If you want to see that again, because it looks fun, I will show that to you. See, the guy is trapped inside. You can't even see its shiny part. So body centered atom, the entire atom is inside the unit cell. ठीक है जी, बढ़िया हो गया. We've learned so much today, right? And in such detail. Edge center. Just for fun, edge center, okay? Basically what's happening on the edge center is this guy. So you have an edge and you have a sphere present in the center of the edge. Okay? Edge center. Fine. So you have to tell me, if there is an atom at the edge center, what will be the contribution of it inside the unit cell? This is something that you have to think about. Okay? This is your homework. Don't worry, in the next class I'll show you the visualization of this also. I'll bring a nice image for you. But imagine, okay, that inside a unit cell, if there's a sphere present at the edge center, you have to imagine the space fill. You don't have to imagine the entire space fill of it. Just imagine the space fill of this particular sphere that is present at the edge center. Okay? How to solve it? Just try to see how many cubes share this edge. Make a cube over here. Pura ek cube bana lo. Make a cube over here. Make a cube over here. I've already solved the question for you basically. That looks weird, but you get the point, right? So this edge is shared in how many cubes? So the sphere over here will be shared in how many cubes? So this is your homework part, okay? Class is not over yet. This is an intermittent homework that I'm giving you. There are lots more questions that are remaining. Chalo. Now we'll solve 3 questions. One of them will be homework for you and then we'll wrap up the class, okay? Questions are important because in exams you have to solve questions. So practicing questions is what actually will help you crack the examinations. Fine. In a face-centered cubic lattice, an atom at the face is shared equally by how many other unit cells? How many other unit cells? An atom at the face is shared by 2 unit cells, one here and one there. But if I'm already talking about one, another one. In a face-centered cubic lattice, an atom of the face is shared by how many other unit cells? It's shared by one other unit cell. This is a question of English, not chemistry. Okay. So a face-centered sphere is shared by 2 unit cells. If I'm sitting in one, the other one is the answer. Cool, simple one. Let's move on to the next case. An ionic compound, this is a more interesting question, by the way. The previous one was just a gimmick. An ionic compound has a unit cell consisting of A ions at the corners of a cube and B ions on the centers of the faces of the cube. The empirical formula for this compound would be very, very simple. Yeah, let's try to make it. Let's try to make the unit cell. So let's make a cube. By the way, the best way to make a cube is something like this. Okay. I'm bad at drawing a cube even in this manner, but yeah, fine. Okay, cube. Now what is given is that there are atoms A at all the corners. So let's make A with blue dots or blue circles or blue spheres, whatever. Okay? So A is at the corners. Now we have B present at centers of faces, basically face centers. So all the face centers you have B. So there's a B at the top, B at bottom, left face, right face, front face and back face. So basically you have B at the face. Fine. So simply we know that in the case of A, you have 8 corners and the contribution of each corner is 1/8. Right? I'll write it for you. You have 8 corners and 1/8 is the contribution of each corner atom. Contribution of each corner atom. See, do you realize the concepts that I've taught you in today's class? I'm repeating them again and again with the help of a question, with the help of a diagram, etc. so that it fits in your brain properly. 8 corners, contribution of each corner is 1/8. So basically, how many A's do you have over here? 1. Fine. Okay. At the same time, B. How many face centers do I have? I have 6 faces. Yeah. So 6, basically I have 6 faces. And what is the contribution of each face center? Half. Half of the atom is inside this unit cell, half of it is cut off. We've seen the beautiful space fill diagrams. So this is the contribution. So how many B's are there? 3. So what's the formula? AB3. Very simple. I'm sure this clarifies any doubts that you had in the contribution part. Cool. More questions like this are there in the NCERT, by the way. You read it and you'll solve it. You'll enjoy it more. This is the last question we'll do together, and a similar question I'll give you. Very nice question. Okay. This is easily JEE Main to JEE Advanced level. This can come in JEE Main also as a tough JEE Main question. This can come in JEE Advanced also as an easy JEE Advanced question. A compound formed by elements X and Y has a cubic structure in which X atoms are arranged at the corner of the cube and 2 atoms Y are at each body diagonal of the cube. Oh, sir, you didn't teach about body diagonal. That's why this question can be a JEE advanced question. Okay. So X atoms are present at the corners, and at every body diagonal, 2 Y atoms are present. Okay. Calculate the total number of atoms in the cube and the formula of the compound. Let's try to draw it, and then I will show you an image also, so that if my drawing skills are not that great, you can understand. ठीक है? तो करना क्या है अपने को यहाँ पे? I am sure putting X is very simple, right? X is just at the corners. So at all corners, we have this blue guy, X. Fine. So how many X are there in this unit cell? Obviously 1. 8 corners, 1/8 contribution of each corner, 8 into 1 by 8, that is 1. So there is 1 X inside this unit cell. That is something that we understand. X is 1. Fine. Now, my dear friends, what about Y? Body diagonal. What is a body diagonal, people? How many body diagonals are there for a cube? Think. This is the food for thought over here. How many body diagonals are there in a cube? Let's try to draw. Okay. Let's try to draw. And you also try to draw it in your notebooks, okay? Don't keep looking at my face and my drawing. Yeah, this is a very modern art kind of a cube. Yeah. So, body diagonal is basically between two opposite corners. This is a corner and this is the opposite corner. Can you see? Two opposite corners. So, if I make a diagonal between these two, that is a body diagonal. Fine. So, how many body diagonals can you think of? Yeah. Try to draw it in your notebooks, people. You can pause the video if you want and then check whether you've drawn correctly. Another body diagonal could be, I've chosen these two corners already, let's choose this corner, and then the opposite one is this. So this is a body diagonal. Yeah, 2 of them are done. Third one, let's try. Some of you already know the answer, I'm sure. Maybe you've done this in geometry earlier, mathematics, maybe you paid attention. Yeah, these corners are done, these corners are done. Now let's take care of this corner. These two will have a body diagonal. Yeah. Can you see what corners are left? These two corners are remaining, right? All the other corners are taken care of. उनका भी बना देते हैं. Fine. And so corner, this is a corner. Oh, ये तो बना लिए. Sorry. This corner basically. This one and this one. So this is a body diagonal. So basically, can you see there are 4 body diagonals? And my dear friends, it is said that at each of these body diagonals, 2 Y's are present. Now you'll be like, sir, but where can these Y's be present? See, whenever such questions come, obviously, as I told you, in a unit cell, in a lattice, you have to take care of symmetry, right? So, to maintain symmetry, if you divide one body diagonal into half, this is half of body diagonal, this is half of body diagonal. So in this half, at the center of this half, there will be 1 Y. Center of the other half, 1 Y. Got it? Symmetry. You have to make symmetry if it is not mentioned. Okay? So this body diagonal, this is the midpoint of the body diagonal. So this half of the body diagonal, there's 1 Y. This half of the body diagonal, there's 1 Y. This half of body diagonal, 1 Y. Getting the idea? So for every body diagonal, there are 2 Y's. Do you realize all the Y's will lie inside the sphere? Andar hai na body diagonal. Body diagonal is inside the body. So the Y's will also be inside the body. So basically, how many Y's are there? 1, 2, 3, 4, 5, 6, 7, 8. So there was 1 X and there are 8 Y's. Answer is, there are total 9 atoms, 1 X atom and 8 Y atoms. 8 plus 1 is 9. If you don't remember 8 plus 1 equal to 9, please smash your head into the wall. And the formula will be XY8. ठीक है जी? Fine. Because Y's are present at all body diagonals. 2 Y's are present at every body diagonal. Can you see? 2 atoms of Y are at each body diagonal of the cube. Now, this is the diagram of body diagonals. Can you see all the 4 body diagonals? They've pointed the body center. I couldn't find any other image, so yeah, bear with this one. But in our question, okay, this is a different question. I'll show you this one also. In our question, Y's were present at these points. Yeah. 8 Y's. 1, 2, 3, 4, 5, 6, 7, 8. Looks much more beautiful than what I showed you, but fine. Yeah. This is a body diagonal. This is a body diagonal. You want me to ruin the entire thing? Cool. So all 4 of these are the body diagonals. So my dear friends, this particular question, same question, I just removed the diagram. This is your homework, okay? It starts with the same. What I solved with you, it starts with the same, but then it makes a modification to that and then asks you, what's the answer? Okay? So pehle to wahi hai. Initial part is what we formed, X, Y, 8. Now in that, we are making a modification over here. ठीक है? So this is your homework question. ठीक है? 2 homework given to you. This is the second one. Cool. So people, finally, let's wrap it up. These are your tasks for the class. I hope you enjoyed the class. So you know, have to hit the thumbs up button, subscribe to the channel, and comment. Definitely comment. You have to comment the answers of the homework questions. Okay? You have to read the NCERT first 15 pages of this chapter. So the first 10 pages we've covered of NCERT. We've covered all the theory related to those first 10 pages. Plus we've learned much more in depth. We've solved a very beautiful question as well. Yeah, you have to solve the NCERT questions as well of the first 15 pages. So the next 5 pages of NCERT, this is what we'll do in the next class, by the way. Please do this. You know, we've restarted Catalysis, and since we restarted it, old audience is already in colleges. So we would appreciate if you could help us get newer audience, because the more people we are able to reach out to, the more sustainable it is for us to run the channel, right? We can't run a business without the audience to contribute to the business. So I'm sure you understand that. We also have to earn our food, and this is how we do so. So please share it with just one friend. Just send the link. Nice class. Maybe that person watches it, maybe he or she doesn't. That doesn't matter. But you do your part by sharing it with at least one friend, please. And then in the next class, okay? So the next class will be on Friday at 7 p.m. And we'll talk about density of solid in the unit cell. What is the rank of a unit cell? What is closed packing? How do you, do packing inside a lattice? How do you build a lattice? And packing efficiency, etc., etc. So these are the points of conversation for the next class. And there's a Telegram group, as I told you, for the PDF notes of today's class specifically. This is the Telegram group, okay? t.me/v_VIP. It's called the Vedantu co-founders group on Telegram, okay? So if you go to Telegram and start searching for Vedantu co-founders or Vedantu only, then this will be one of them, okay? Link in the description, by the way. Fine. So people, we learned a lot about solid state today, and I'm sure I have taught you in a way that no other teacher has till date, at least on YouTube, for free. So if you enjoyed my style of teaching, make sure you hit that thumbs up button, stay subscribed to the channel. You know what to do. I'm going to see you in the next class. That's on Friday at 7 p.m. Bye bye until then. Take care.